Okay, in this example, we're going to be dealing with a single population, but two sets of data from that single population. A fitness trainer claims that high-intensity power training decreases the body fat percentages of females. The table below shows the body fat percentages of 8 females before and after 10 weeks of high-intensity power training. At alpha set equal to 10%, is there enough evidence to support the trainer's claim? Assume the samples are random, dependent, and that the population is normally distributed. So this word dependent is kind of a flag that you're looking at paired data. When you look at the table here, it seems obvious you're dealing with a population of females. You're looking at a measure taken before and after the training. When you are dealing with dependent data, you will not be calculating with this raw data. You are going to be calculating with the differences between these pairs. So I need to show you how you get that. Once we find the differences, well, actually you can find the differences by subtracting them yourselves, but then you need to find the mean, which isn't very hard to do, but then you also need to find the standard deviation, and that is that long, really drawn out formula that I want to show you how you can use the StatCrunch to do it for you. So once you've used StatCrunch to get that information, to do this by hand, you would also need to use the formulas on our formula page. Let me go ahead and get started finding the summary data. I'm going to open up StatCrunch here, and I already have our raw data put in our two columns here, var1 and var2. And again, you can calculate the differences yourself and enter them here in var3. But I want to show you how you can get StatCrunch to do that quickly for you. So I need to click in this first cell in var1 column. Then I'm going to hit click on data, on down to compute, and then over to expression. So in the expression cell, I want to put in my formula. It's var1 minus var2, and then I need to hit compute. And I don't know why that first one gives a rounded off version, but once you click outside that, it gives you what you need. So we've created a column here with those differences. Once we've got that, then we can do the process that we learned in Chapter 3, where you go into Stats, Summary Stats, and Columns. And because I'm going to be calculating with these differences, that's what I'm concerned about, I'm going to click the column var1 minus var2. Then I can just move on down to Compute, and I will get all of that summary data. What I'm most interested in is in the mean here of 0.2625. and our standard deviation of 0.56299, that would round down to 0.563. So we need to remember that because I need that information once we get rolling here. So I'll try to slide that down. Okay, so I need to get started with setting up our null hypothesis and our alternative hypothesis. And we also have some new notation, so it gets a little bit confusing. Remember that our null hypothesis always has the equality sign. And so we're going to set our null hypothesis is that the mean of the differences, that's how you read that symbol right there, mean of the differences is equal to 0. In other words, some are above, some are below, but they all average out to be a difference of 0. Our alternative is going to be that the mean of the differences is greater than 0. That's assuming that we take before minus after. And so back up here I underline decreasing. And that decreasing is usually an indicator that, oh, this is going to be a less than, this is going to be a left-tailed test. But when you think about it, the claim is that this decreases body fat so that your before body fat would be higher than your after body fat. So if I would assume before minus after, that means my differences, the mean of the differences, could possibly be greater than 0. So be aware and really read your problem, make sure you're comprehending, so that you get the right sign here. So going into our fourth step, our confidence level is 90%, and I know I'm running out of space here, and I'm getting that 90% from the alpha of 10% alpha, which we've listed here. We know that this is a right-tailed test because we're thinking the difference between the before and after is going to be greater, that it was more before than it was after. Our degree of freedom is 1 less than our sample size, so our degree of freedom is 7. Our critical value is 1.415, and I want to show you where I found that. I'm getting a lot of windows opened here. But I'm going to open up our t-table, and again, remember we are doing a one-tailed test where we are doing 10% alpha, so that's going to be our first column. Our degree of freedom was 7. So when I look at where the row 7 intersects with the column for 10% alpha and one tail, we get this 1.415. So back to this. When I plug everything into our test stat, I'm going to be using this formula. So once again, I'm opening up another table here. So I'm going to open up our formula page. When I go to the formula page looking for under hypothesis tests for means, I'm going to be looking at this formula right here. We will not ever use this formula here because we will never be given that information. So we're looking at our T stat is equal to, I'm sorry, I'm at the wrong one. Down here, our T stat is going to be equal to the difference, the mean difference of our samples, minus what we're projecting the population mean difference to be, divided by the quotient or the division of our sample standard deviation of the differences divided by the square root of n. And I know that sounds, even though it's a small formula, every single item there is almost a new notation here. So I think it's going to be most comfortable if we just do this example and how that all fits in. Okay, so here's our formula. I've written it all down. Remember our, plug this up so you can see this. Okay, our summary statistics in StatCrunch told us that we had a mean of 0.2625. So that's what our D bar is. It is the sample mean of the differences. So 0.2625 minus 0. That is what our null hypothesis is that the mu of D is equal to 0. So that's why I'm plugging that in there. So our standard deviation of the differences is down here from our summary statistics, the 0.5629, which is going to round to 0.5630, divided by the square root of the sample size, which is n. So hopefully that will make sense to you. You shouldn't have to worry about parentheses on this one. It's pretty straightforward. There's not any sum or minuses. You know, once we're subtracting 0, that just really drops off. So being there's no sums or minuses going on in our formula, you can just put it into the calculator. But I guess I would put this denominator in a set of parentheses just to make sure that that's calculated as one denominator, one term. Okay, then we need to do our critical value or p-value and our confidence interval. So when I draw the t distribution here, I can put in my confidence or my critical value of 1.415 and our test statistic, which is just a little under that, 1.319. We can see that that is not in the rejection zone, so it looks like this is not significant. There's a little bit of a difference there, but it's not significant at that 10% alpha. We're doing our p-value. The test statistic of 1.319 is left of all the columns on the t-table, meaning that the p-value is greater than 0.1. So again, I want to go to this to show you what I mean. Again, we're looking at the row of 7 because our degree of freedom was 7. And I'm looking for that 1.319. Where would that fall on here? And I can see that it's not going to fall anywhere. It's actually going to be to the left of the 1.415, which is our critical value. It's to the left of that, which means it is greater than 0.10. In other words, 10% probability. So that's how you can use the table. So going back to this, StatCrunch would have shown us that our p-value was equal to 0.1144, and I want to show you how that would work, but we can see that that is going to be higher than it's going to be higher than our alpha of 0.1. Then for the confidence interval, again, we're using some of the similar components, but again, you can find that on the formula page. The mean difference plus or minus our alpha times the division or the quotient of our difference of the standard deviation of the differences divided by the square root of the sample size. So I plug all this in, I end up getting a confidence interval where I have a negative on the lower range, the lower limit, and the upper limit is positive. So automatically we know 0 is in that interval. We can't possibly reject this null hypothesis of U of D being equal to 0 because 0 is in this interval. So our decision is to fail to reject the null hypothesis. There is not enough evidence to support the claim that this training decreases body fat. So all three of these report to fail to reject. Because our claim was our alternative, we're saying that there is not enough evidence to support that alternative, which is stating that this training decreases body fat or that there's a change. Okay, so you definitely, I'm sure, want me to show you how to do that in StatCrunch. And lucky for us, there's two different ways that we can do this. I want to show you how this formula is utilized in StatCrunch. So I'm going to use all the space here. I'm going to take our summary statistics and set it down here. And I'm going to go in here to stats. And actually what I want to do is I want to treat this as a one sample mean problem where I'm just looking at the differences between these two. So I'm going to go into stats. I'm going to look at T-stats, one sample with summary, because I'm going to use this summary information that we have down here. So our mean sample was, our mean from our summary stats was 0.2625. Our standard deviation was this 0.563 is what that would round to. And our sample size was 8. Okay, and I'm going to do a hypothesis test, and our alternative again was, remember, the difference was greater. So I'm going to go ahead and click compute, and I find that we have a p-value of 0.114, so that was how you can find the exact p-value. We can see our degree of freedom matches up, it was 7. Our mean matches up. All that information there was derived from just looking at doing a hypothesis test on the differences of those means. Okay, or the differences between those two data sets or those two samples. Okay, another way that I can do this, and this is actually using the outline that I identified at the top of this activity. In StatCrunch, you can enter you will always have to enter the data in the columns, but this is an alternative way that you can do this, and really much, much faster. So we're going to select Stats, T-stats, and Paired. So I'm going to go ahead and click Stats, T-stats, and now I'm going to go down to Paired. This is only used with paired dependent means. So here you can see it's asking me to identify what columns do I want to use for sample 1 and sample 2, and that's going to be var 1 and var 2. So I don't have to do any previous calculating or anything with this method. I'm going to go in here and continue to use that the mean is, our alternative is that the mean difference is greater than 0. And I click compute, and it really gives us the same outcome that we had before. So you can see these two outcomes are really, really similar. Okay, I'm just going to show you on the one where you can go back in and edit. This time I can go down to do the confidence interval, and because this is, we were doing a one-tailed test and it was a 90% confidence level, well, the interval that has 10% in each tail for an interval would be 0.8. So you have to remember that when you're doing a one-tailed test at a 90% confidence level, you're looking for 10% in that one tail, that right tail, for the hypothesis test. Well, the confidence interval that has 10% in that right tail as well as the left one would be an 80%. So you have to make that adjustment on there. And we can click compute, and we end up with our confidence limit, our lower limits and our upper limits that are just a little bit different than what we calculated. We had 0.192, I think, or 1.91 is what we have here, and 0.5441 here, and I think we had 0.5442. I'll close that up, and we can see that, yeah, there was a little bit of difference, and that is because I had to round here, and possibly at the denominator here there was some rounding that we needed to do, whereas that's not happening in StatCrunch. So StatCrunch is going to be more exact. Hopefully that gives you really two different ways of doing that, and then I just want you to know that if you do the hand work here, you either need for me to give you the mean of the differences as well as the standard deviation, or you need to calculate that using this step up here using summary statistics.